Hello, beautiful people. We're on chapter 16, adaptive immunity. This is one of my favorite topics, one of my favorite chapters. It is just full of information. And I got to tell you, the quiz you're going to take doesn't even scratch the surface of the iceberg. I mean, I just can't do this justice, okay? So the assessment is pretty trivial compared to the amount of information that we have on this topic. So let's get started. The hallmarks of adaptive immunity, okay? I kind of alluded to them earlier. You have innate immunity and adaptive immunity. The hallmark of innate immunity is that it's going to be broad in a spectrum and what it's going to pursue, but is going to be fast, okay? With adaptive immunity, its effect is slower. It can be days to weeks, okay? However, it has the effect that it is very, very specific. So once adaptive immunity decides that it's going to launch an adaptive immune attack against a particular organism, in theory at least, that organism is doomed, okay? So here's the 5 attributes of adaptive immunity. Specificity, okay? Specificity, because we're either going to use cytotoxic T cells to kill cells that we know are infected, or we're going to use antibodies whose specificity against antigens is incredible, okay? Either way, the adaptive immune response is said to be surgical in nature. In other words, it's going to be very specific as to what it is that it goes after and attacks. It is inducible, okay? So that means that it is not patrolling around as the way that the innate system is patrolling. It needs to be induced. Consequently, the adaptive immune response depends on the innate immune response, in particular, professional antigen-presenting cells such as dendritic cells and monocytes and eosinophils, in order to be induced and activated to attack a particular pathogen, okay? It has clonality, and this is fantastic, okay? So once you have a cytotoxic T cell that is activated, it undergoes what's called clonal expansion, which means that literally millions and billions of clones are produced, all seeking out and destroying that one pathogen, okay? So the effect is it's not multiplicative, it's exponential, it's huge, okay? So clonality is fantastic. Unresponsiveness to self, well, we want it to be unresponsive to self, okay? We want an adaptive immune response to only recognize and consequently go after antigens that are not recognized as being part of our body. As you well know, that is not necessarily always true. Consequently, we sometimes have autoimmune responses, and that causes a lot of problems, okay? But typically, in a healthy individual, the adaptive immune response is not responsive towards self-antigens. And then another wonderful hallmark of the adaptive immune response is the fact that it has a memory, okay? So what does that mean? That means that if a certain infection attacks you and the adaptive immune response happens to be launched, you end up with memory cells that remain residual for weeks, months, sometimes years. And the effect is that if you ever end up with the exact same infection again, those memory cells will activate the adaptive immune response much more quickly and at a higher level of effectiveness than during the first infection. As a matter of fact, it is this hallmark of adaptive immunity that we take advantage when we use vaccination. We're literally launching the adaptive immune response and creating memory cells so that if you actually become sick with the actual pathogen, the adaptive immune response can react quickly and ferociously, okay? So very, very neat things. There's two arms to adaptive immune response, okay? There's the cell-mediated or the T lymphocyte-mediated arm. And again, the purpose of the T cells is to create what's called cytotoxic T cells. Cytotoxic T cells, their whole job is to seek infected cells in your body. They're displaying the antigen of infection, effectively telling the cytotoxic T cell, I'm infected with this particular pathogen. And then that cytotoxic T cell is going to associate with that infected cell and is going to induce cell suicide, which in the last chapter we introduced as the word apoptosis. Apoptosis, okay? So that's the cell-mediated arm. The other is what we call the humoral arm, okay? In the humoral arm, we're talking about B lymphocytes because they're the ones that produce the water-soluble antibodies, okay? And that's why it's called humoral, because the antibodies are in the humor, in the liquid, which happens to be blood, okay? So we have the cell-mediated arm and we have the humoral arm. And so adaptive immunity depends on basically lymphocytes, and those two lymphocytes are, again, T lymphocytes and B lymphocytes. Okay. There's a nice little picture of a lymphocyte. I can tell you that it's not activated. How do I know that it's not activated? Because it's all nucleus and very, very little cytoplasm. When a lymphocyte is activated, the darn thing becomes very large, either because it's cytotoxic and is producing the enzymes necessary to carry out cell suicide, or because it's becoming very large in order to release antibodies, and so the entire cytoplasm becomes rough endoplasmic reticulum as it produces antibodies as fast as it can in order to defend our body, okay? So that's the picture of an inactive lymphocyte. Okay, so when we're talking about adaptive immunity, we have to introduce what's called the major histocompatibility complex, or MHC, okay? And historically, this came from the fact that physicians were carrying out grafts of skin and other tissues from one person to another. And there was graft rejection. And they could not understand why one person would reject a skin graft from a different person. And after a little bit of investigation, they found out that each cell in our body has a specific receptor, okay? And we called it MAC, Major Histocompatibility Complex. In other words, that receptor on that cell is what identifies that cell as belonging to my body. And if I have another cell from another person, that MAC receptor is going to be different, and therefore my body is not going to recognize that receptor, and my body is going to try to reject this cell because it's displaying the incorrect histocompatibility complex, okay? So histo means tissue, okay? So it is this receptor, the histocompatibility receptor, that tells my body whether this cell in this tissue is compatible with this cell in this tissue because of these receptors, which we have named the major histocompatibility complex, okay? So that's the history behind it, okay? What do we need to know? We need to know that there's two classes of there's two classes of MAC. There's MAC1 and MAC2, okay? The major histocompatibility complex 1 is in every cell in your body except for red blood cells, okay? That MAC1 is important because that allows the cell to communicate that it's infected. So if your cell becomes infected, it will pop out with a receptor called the MAC1, class 1, saying, sorry guys, I'm infected. Can somebody please help me die? Can somebody kill me? Okay? So every cell in your body, except for red blood cells, has that MAC1 because every cell in your body has to have the ability to tell somebody when they become infected and when they should be deleted from your body, okay? That's MAC1. MAC2, on the other hand, is only present on what's called professional antigen presenting cells. So those are the white blood cells in your body, okay, whose sole purpose is to consume a pathogen, break it apart, take the antigens out of it, okay, and then present it on a receptor called an MAC2 receptor. And what that professional antigen presenting cell is doing, it is not telling somebody that is infected, because it is not. What it's telling somebody is, hey, I just killed this pathogen, and this is what it was wearing. So if you find this, please kill it, because it doesn't belong here. That's an MAC2, okay? So again, MAC2 is only present in professional antigen presenting cells. And when we talk about professional antigen presenting cells, the main guys that we're talking about are macrophages and dendritic cells. They're not the only ones that present antigens. They're not the only ones. Okay, all phagocytes present antigens, but these are the ones that usually show up to the location of infection and carry out MAC2 antigen presentation first. Okay. All right. So this is what MAC1 and MAC2 looks like. As you can see, they're very, very similar. MAC1 has only one hydrophobic leg that allows it to stay embedded in the cytoplasm of the antigen-presenting cell. MAC2 has two legs. Do you need to know that? I don't think so. It's not a big deal. Here's the T cell receptor. Okay. Do we need to know this? Well, just to the extent that you know that a T cell receptor is going to be necessary in carrying out the function of cytotoxic T cells and regulatory T cells. Okay. Okay. So here's the T cell. Something that you need to understand about the adaptive immune response is that it's a three-tier event. Okay. The first tier is the innate immune system that we just talked about, which means professional antigen-presenting cells such as monocytes and dendritic cells consume and present via MAC2 and antigen. Okay. That then goes to the T cells. T cells first. Okay. Why T cells? Because T cells are the ones that can wake up other T cells or activate other T cells, and T cells are the ones that can wake up or activate B cells. So it always goes dendritic cells and monocytes, then T cells, and then B cells last. Okay? Innate immune system, adaptive. So, how many types of T cells are there? There's cytotoxic T cells. Cytotoxic T cells is the actual T cell that does the job. What job is it? To find infected cells in your body and help them commit self-suicide. That's the role of the cytotoxic T cell. Then you have the helper T cell. The helper T cells comes in two flavors. You have a type 1 and a type 2. This is easy to remember, guys, because as I just said, the first thing that gets turned on is the T cell, And then the second thing that gets turned on in the adaptive immune system is the B cell. So a T cell is number one, the B cell is number two. That means that you need helper type 1 to turn on the T cell and helper type 2 to turn on the B cell, okay? That's why we have two helper T cells, because it is these T cells that turn on everything, okay? And then you have the regulatory T lymphocyte, and what that does is it makes sure that the adaptive immune response doesn't exceed a maximum. Okay, like I said, one of the hallmarks is clonal expansion. It would be very easy for T and B cells to just multiply indefinitely. We can't have that, okay? It has to be enough to resolve the infection, and that's enough. So these regulatory T cells, they're there to make sure that there's an upper maximum to the clonal expansion of these activated T and B cells. Okay, I just wanted to show you this because if you're talking to somebody who has HIV, HIV attacks leukocytes that have CD4 receptors. CD stands for cluster of differentiation. You don't need to know that. What would be nice to know is the fact that helper T cells, take a look at this. Helper T cells, type 1, which activate T cells, and type 2, which activate B cells, they're both CD4 cells. And it is this type of cell that HIV attacks. Hopefully you understand why this is a big deal. If helper type 1 and 2 of the T cells are undermined by HIV, they cannot activate cytotoxic T cells or B cells into lymphocytes, and that effectively wipes out the adaptive immune response. This is scary stuff, okay? The regulatory T cell, as you can see, is also a CD4 cell. The cytotoxic T cell is a CD8 that typically does not get attacked by HIV. Okay, so when a patient that happens to have HIV goes to their physician, the first question out of their mouth is, "How's my CD4 count?" Because if it's high, they have an immune system. If it's low, they do not have an immune system. Okay, so now we're going to go into how we activate these T and B cells. We're going to start with T cells. Makes sense because they're the first ones that are activated. And the first thing that we go through is what's called clonal deletion. Okay, so one of the things that you need to know is that the T cells are deleted in the thymus, and B cells are deleted in the bone marrow. Okay. And this is incredible stuff, okay? Effectively, you have a T cell here. You have a, oh, here we go, perfect. Effectively, you have a stem cell. This is T cells, okay? So that means that the stem cell is in the bone marrow, but then once it's in the bone marrow, it will travel to the thymus in order to mature, okay? And this is what gets very, very interesting. That T cell produces T cell receptors indiscriminately. It just makes all the T cell receptors that your genome can produce, okay? And then what happens in the thymus is you have a two-step test. The first test is, do you recognize your own major histocompatibility complex receptor? In other words, do you recognize your own tissues as belonging to you? If the answer is yes, then this guy continues to live. But if the answer is no, then we delete it. we destroy it. Apoptosis takes place, okay? Now, notice that not only do we have the major histocompatibility receptor here, but we also have epitopes. What is an epitope? An epitope is a molecule. For another way of describing it would be it is an antigen, okay? It's something that T cells and antibodies can recognize. And what the thymus is doing, okay, is it is producing all these antigens for self. And, oh, sorry, I just got a knock on the door. Sorry about that, guys. So, as I was saying, if we recognize the MHC, the major histocompatibility complex, then the cell survives. If it doesn't recognize self, that MHC, then the cell undergoes apoptosis. But what you have to note is that that MHC complex is holding antigens from your own body. As a matter of fact, they're called autoantigens because they're self-antigens. And if the cell, okay, recognizes the self-antigen, it means that it would attach to a cell that has that antigen and kill it. You can't have that happen. So if it recognizes the autoantigen, okay, then that cell must be deleted, okay? If it does not recognize the autoantigen, then it becomes what we say part of the repertoire of cytotoxic T cells, okay? So this sounds a little bit confusing, but like I said, it's a two-step event. Number one is, do you recognize MHC? You have to be able to recognize MHC because all of our own tissues have the same MHC receptor. If it recognizes it, we stay alive. That's the first check. That's here. The second check is, do you recognize self-antigens? Do you recognize things that belong to my body? If that's true, then you need to die because I cannot have a cytotoxic T cell recognizing my antigens, because if it does, then that T cell can launch an autoimmune response and attack my own tissues. That can't happen. So in the second check, if it recognizes autoantigens, then it is deleted. If it does not recognize autoantigens, then that would imply that it only recognizes foreign antigens, and that's the only thing it would attack, so that it becomes part of our repertoire. Again, as the author says, some of these that do recognize autoantigens, some of them become regulatory T cells. So there's a clonal deletion taking place in T cells. And again, the purpose of the clonal deletion is to make sure that the T cells that remain in our body are those T cells that will not recognize our own antigens. And that way, when they are deleted, the remaining T cells will not attack our own body. There will not be an autoimmune response. That's clonal deletion. This also has to happen with B cells. Okay. With B cells, what you need to know is that when you activate a B cell, it becomes a plasma cell. And the role of a plasma cell is to produce antibodies. Okay, so that's the main point here. So an antibody is effectively a B cell receptor that the B cell produces and releases into the bloodstream. Okay, so here's a B cell receptor. And as a matter of fact, the only difference between a B cell receptor and an antibody is that the B cell receptor has this little thing that tethers the antibody to the plasma membrane of the plasma cell. If this was not here, the remainder of it would be an antibody. Okay. Here's an activated plasma cell. When you have an activated B cell, it's called a plasma cell. This is incredible. Look at the cytoplasm. This entire cytoplasm is nothing but rough endoplasmic reticulum. And the reason for that is because it's producing antibodies as quickly as it can, okay? So that's a plasma cell. Let's see. We need to talk about the antibody. It couldn't hurt to know the parts of the antibody, okay? So let's go over this real quickly. First of all, this antibody consists of 4 parts: 2 heavy chains and 2 light chains, okay? The heavy and light chains are tethered to each other through what's called disulfide bonds, okay? This is the amino acid cysteine, because these are sulfur-sulfur bonds right here. And the heavy chains are tethered to each other by the same interaction, disulfide bonds, okay? 1 there and 1 there. So 4 components, 2 heavy and 2 light, okay? Tethered to each other by disulfide bonds. We have the antigen binding site. This is the part of the antibody that recognizes the antigen. It is important for you to understand that the antigen binding site consists of the variable region of the light chain and the variable region of the heavy chain, okay? So both of these together form the antigen bonding site. What else do we have? We have this whole thing, the antigen binding site plus the rest of that Y is called the arm. This part right here is called the hinge because it literally functions as a hinge. So you have your antibody like this, and the arms can literally move closer or further away from each other. So it functions as a hinge. And then the rest of it is called the stem. F sub C stands for a crystallizable fraction, because they've done X-ray crystallography on these things, and this is the part that they make a crystal out of, okay? And the heavy chain is actually important because the stem is a part that's going to let you know how that antibody functions. So we're going to see that in just a second. Antibodies can do a lot of really neat different things, and it is a type of stem that's on there that dictates how that antibody is going to function. Okay, so look at this. Isn't this beautiful? I mean, when you look at the defenses in our body, it's a wonder that we can even get sick. This is how antibodies function, okay? There's activation of complement and mediation of inflammation. There's neutralization, there's opsonization, killing by oxidation, agglutination, and antibody-dependent cellular toxicity. So let's go through these one at a time, okay? All this talking makes me thirsty. Okay. So activation of complement. Do you remember complement last chapter? What does complement do? Well, if you remember, there's 3 main things that complement does. Number 1, it makes the MAC, the membrane attack complex. That membrane attack complex makes pores in the membranes of bacteria and effectively kills them. That's one thing that it does. What else does it do? Well, it can function as a chemotactic factor, causing bacteria to be attracted to the area of infection, okay? What else can it do? It can mediate inflammation, okay? Those are a lot of things. So anything that can activate the complement is going to do great things for the immune response. And what happens is that with certain stems in antibodies, the purpose of the stem is to initiate the complement cascade. If it gets, if the complement cascade gets initiated, that means that a whole lot of bacteria are going to end up with holes in them, and the mediators of inflammation are going to ensue, and consequently, the site of infection is going to end up getting all the resources that it needs in order to resolve that infection. So that is a fantastic thing that an antibody can do. What else can it do? It can do neutralization. This is incredible. You guys must be tired now of hearing if the microorganism cannot attach to the cell, you cannot get infected. So there's antibodies that can be specific for the receptors on these pathogens, and if they attach to the receptors of the pathogens, that pathogen cannot attach to the tissues. You have effectively inhibited the infection. As a matter of fact, I think in the summaries, you'll see, or maybe in the news, I'm losing track of all this stuff that I'm putting up for you guys, but it talks about the young ladies from South Africa that produced antibodies against HIV, and consequently they cannot get infected by that virus. Can you imagine? That's fantastic. If you can make antibodies against this virus, you can effectively walk through a ward of infected patients and you cannot be infected. That is neutralization. Neutralization is when the antibody attaches to the receptors of pathogens, whether they're viruses or bacteria or parasites, and inhibits the ability of that pathogen to attach to and enter a cell or a tissue. That's neutralization. Opsonization is very cool as well. Okay, I use a lot of war metaphors in this chapter because at the end of the day, this is war. This is a battle between our defenses and pathogens. Okay, so in opsonization, the metaphor that I like to use is, when we go on these police actions in the Middle East, we send these scary little guys called Rangers. Okay, these scary little guys use what's called, this is horrible, I know, but unfortunately it fits very well. They use these things called smart bombs. Okay, they're called smart bombs. Why are they called smart bombs? Because the bomb doesn't go wherever it wants. It goes specifically to a target. Okay, and you might ask yourself, how is it that that smart bomb, chooses where the target is at? Well, what happens is the Ranger has what's called a laser gun, and they paint the target with that laser. And the smart bomb follows where that laser is at, and it hits that target and nothing else. Okay? So as horrible as this metaphor is, that is exactly what opsonization is. Okay? So opsonization is when you have a pathogen, you have an enemy of some sort, the antibody attaches to that pathogen and it paints it for attack. Once that antibody attaches, that stem yells to all the adaptive immune response and goes, hey guys, you see what I'm attached to? Come here and destroy this thing. Okay? So very, very effective, incredibly effective. Okay? Another one that I love, which I think is interesting, is what's called killing by oxidation. So I don't know if you guys remember, but we went through all these different toxic forms of oxygen, and we said that a lot of pathogens cannot, they can't live in the presence of oxygen or toxic forms of oxygen. Okay. Well, as it turns out, some antibodies have a stem that functions as an enzyme that produces these toxic forms of oxygen and consequently that toxic form of oxygen attacks whatever the antibody is attached to and kills it. Incredible. So this stem can function as an enzyme, as a machine forming something toxic to kill that pathogen. Incredible. Agglutination. Agglutination is an interesting one. If you guys have ever been in school and you did blood typing and you added monoclonal antibodies to your blood and the blood clumped up, that's called agglutination, okay? So what's going on is you have your antibody, okay? The antibody has not one, but two antigen recognition sites. And because of that, one bacteria can get here, another one can get over here, but then another antibody can get here, and then another bacteria can get here, and then, so effectively you end up with this chain of alternating antibodies and antigen-containing bacteria. It's a polymer, and because it becomes a chain, it becomes heavy, it cannot stay soluble in your blood, and it precipitates out of the blood. Is that a good thing? Yeah. Because once it's not in the blood, now the tissues can focus on that agglutination and take it out of service. Okay, so that's agglutination. And then we have what's called antibody-dependent cytotoxicity, and that is incredible because what's happening there is that the stem is attracting natural killer lymphocytes. Okay, so remember how we said earlier that natural killer lymphocytes are part of the innate immune system, and their main role is to kill virally infected cells and tumor cells whose surface proteins are not recognized by our body. Those were the two main roles that we attributed to natural killer cells. But thanks to antibodies, that natural killer cell can also come in and attach to anything that antibody is attached to and kill it. So it means that it can also kill bacteria. Okay, so this slide right here provides an illustration of what we've been talking about. Okay, here's neutralization. Okay, so as you can see, you have antibodies attaching to receptors of a virus or a bacterium. When that happens, it prevents attachment and consequently infection. Here is showing a toxin. Okay, that toxin can be snake venom, for example. So these people who had their lives saved by antivenom was being injected into their body are antibodies that are specific for that snake's venom. Okay, so antibodies as a antivenom can function as a life-saving event in an emergency. That's how important this is. It is a difference between life and death, and it's something that functions immediately. So adhesion is very important. Here's opsonization. Remember, opsonization is to paint an object for destruction. So we painted this bacteria, and now this phagocyte has found it and is going to consume it. Here's oxidation. Oxidation is when the stem functions as an enzyme, producing toxic forms of oxygen to kill the bacteria. Here's agglutination. See the chain? So each antibody has two antigen recognition sites, right? One here and one here. So it means that we can have antibody, bacteria, antibody, bacteria, antibody, bacteria. As you can imagine, this becomes very heavy. And again, it precipitates out of the blood, and it makes it easier for phagocytes to find and destroy it. And then here's our antibody-dependent cell-mediated cytotoxicity. You can see that the antibodies are attached to a bacteria, okay? And the stem attracts natural killer lymphocytes, which are supposed to be part of the innate immune system. So this is fantastic. This is the adaptive immune response using protagonists of innate immunity in a very specific manner. How beautiful is that? So now we can actually use protagonists such as natural killer lymphocytes, which are supposed to be generalists, very specifically because of the ability of antibodies to have them come be attracted and carry out the apoptosis of that cell. Incredible. See that perforin? That perforin destroys the bacteria. Lysis destroys the bacterial cell. Okay, I'm gonna halt there for a second, I think. I'm trying. Okay, so we're just talking about the functions of antibodies. Now we're going to talk about the classes of antibodies. It turns out there's multiple classes, and they're manufactured by plasma cells at different times, okay? So these are the different types of classes. Immunoglobulin M, G, A, E, and I don't care if you know D. D, we don't really know what it does yet. And this is what I would like for you to remember about it. Immunoglobulin M is known for being the first antibody that is produced, okay? And then the plasma cells go through what's called a class switching. So it goes from IgM to IgG, okay? IgG is important because it is, as the author says, the most common and the longest lasting antibody. So this is the one that does the heavy lifting, okay? And then you have immunoglobulin A. This is interesting because this is how passive immunity goes from mother to infant, okay? A lot of people make the argument that mothers should breastfeed their infants, otherwise the infant is not going to have any immunity. And as it turns out, that's actually true, okay? Immunoglobulin A is actually present in tears, is present in breast milk, to some degree is present in saliva. And when a mother breastfeeds an infant, that infant gets that passive immunity from the mother as it receives immunoglobulin A through milk, okay? Immunoglobulin E is important because it works with eosinophils in order to resolve parasitic infections, okay? And what's interesting is what they look like. Look at immunoglobulin M. It's a pentamer, okay? It's a pentamer. It's 1, 2, 3, 4, 5 antibodies arranged in a five-sided motif. This is very, very large, okay? So one of the things that's interesting about immunoglobulin M is that, for example, if a mother becomes infected against some infection, and the mother produces IgM, that IgM is so large that it will not cross the placenta, okay? It has to wait until the mother does a class switching from IgM to IgG, and then that immunoglobulin G can actually traverse the placenta. So if the mother has an infection of some sort, she's going to resolve her own infection before her unborn infant can resolve it. So that's a problem. Here's IgA. IgA has a tendency to be a dimer, okay? But it can also be a monomer. So the most interesting one, in my opinion, is this IgM that is a pentamer. All right. We're going to go into clonal deletion of B cells. We've already discussed clonal deletion of T cells. We've already discussed why this happens. Okay, we cannot have T and B cells react against autoantigens. If they do, then they could have the ability to launch an autoimmune response, and we can't have that happen. So we have to have clonal deletion of T cells because they're activated first, and then we're going to have clonal deletion of B cells because they get activated second. So here's our stem cell in the bone marrow, okay? We end up with a repertoire of B cells, each one with a different a B cell receptor that will be the future antibodies, okay? And now they get one check, and the check is against the cell's autoantigen. And you might ask yourself, what? Why does a T cell have to go through two checks, MHC and then autoantigens? And then here's this B cell, and it only has to check itself against autoantigens. It doesn't have to check itself against MHC. And the short answer is no. And the reason is no is because in order to activate this B cell into a plasma cell, we need a helper type 2 T cell, which has itself already been checked by MHC. So the great engineer, when he or she designed our immune system, decided to omit this redundancy of checking the MHC a second time with B cells because, again, the guy that's going to activate the B cell into a plasma cell has already been checked with the major histocompatibility complex, okay? So this guy only gets checked against autoantigens. Again, if it recognizes it, boom, apoptosis. If it doesn't recognize it, then it goes into the blood and it travels to the spleen where it waits to be activated if it needs to be activated. Okay, we need to introduce the concept of cytokines. And the reason for this is because cytokines is the way that white blood cells are attracted to the site of infection, okay? Chemotactic cytokines. So those are released by white blood cells, again, specifically to attract even more white blood cells to the site of infection. So cytokines is a molecule produced by cells and typically is done to chemotactically to attract additional white blood cells. What other types of communication are there? Well, there's interleukins. We're going to see why interleukins are important in just a second here, okay? Because interleukins play a major role in clonal expansion. So we've already covered clonal deletion, getting rid of everything that has an autoantigen. Now, when a cell gets activated and we need it to undergo clonal expansion, okay? In order for that to happen, we need communicators such as interleukins. So these interleukins are essential for signaling in between the white blood cells. Interferons, we're going to cover that in a second. Okay. Actually, no, we already covered, right? We already covered interferons in the innate immune system. We have growth factors. These are important because they drive the growth and division during the clonal expansion, very important. Tumor necrosis factor, fantastic stuff. This is stuff that's, again, released by T cells, and they are responsible for killing any cell that has peculiar surface antigens. We're talking about cancer, right? So this is important. You have a whole bunch of summaries that address this point because what we're doing right now with T cells is that we're taking them out. We're programming them to attack specific types of cancer in our body, and they were putting them back in the body. Okay, so you have a summary that addresses this. I hope you chose one of them because it's just fantastic. Okay, and then chemokines, like we said, is just a messenger that causes white blood cells to move from one point to another chemotactically. Okay, so let's go. I like the pictures. The pictures are very useful. Okay, so what are we going to do here? We are going to activate a cytotoxic T cell. Okay, so I mean this gets a little bit complicated. So what are we going to start? We're going to start with a dendritic cell or a monocyte. Remember, these are the professional antigen presenting cells. Why do we call them that? Because they're the only ones that carry MHC2, major histocompatibility complex 2. Okay, so this dendritic cell consumed a pathogen of some sort. It broke it apart, and then it went to present with not just MHC2, but also MHC1. Okay. Now there's a reason for that, and that reason is that cytotoxic T cells only have an MHC1 receptor. Why is that? Well, remember, their job of cytotoxic T cells is to kill infected cells. And how do infected cells tell you that they're infected? They tell you by doing an MHC1 presentation. So therefore, the cytotoxic T cell only needs an MHC receptor to recognize that MHC1 from the infected cell. So therefore, cytotoxic T cells only have an MHC1. However, helper T cells, what kind of a helper T cell? A type 1. Why a type 1? Because we're activating cytotoxic T cells. If it was a B cell, then it would be a type 2. So here's a helper T cell. It is being activated by a professional antigen presenting cell with an MHC2 with the epitope of the pathogen that we're going to seek and destroy. Okay, so this whole association here is called an immunological synapse. So there has to be two immunological synapses. One here, MHC1, notice that because this is a cytotoxic T cell, it also has a CD8. Okay, you can imagine that this one's going to have a CD4 because it does. Okay, and the redundancy is incredible. Why? The adaptive immune response has to be very redundant in its checks, because once you launch it, there's no way to stop it. Okay, it's like the codes to the missile silos. Once they're on their way, you're in trouble. So before you launch the missiles, you got to make very, very, very certain that you want this to happen. Okay, and the way that this is done is by redundancy over redundancy over redundancy of checking. So here, the MHC1 CD8 synapse activates the T cell. Okay, once this gets activated, that means that that T cell is ready to do something. However, it has not gotten the signal to undergo clonal expansion. Over here, the helper T cell is getting an MHC2 synapse, CD4, and the redundancy is that an interleukin 12 signal has to be released by the dendritic cell, and when these two signals come about, then this helper T cell differentiates into a type 1 helper T cell. Otherwise, it doesn't happen. So how redundant is this? It's ridiculous. You need to have an MHC2 with a CD4 with an interleukin 12, and we have all of those three things going on. Then we'll have differentiation of the helper cell into type 1. Otherwise, nothing's going to happen. Wow, how regulated. Over here, we have an MHC1, okay, with a CD8. See the CD8? the immunological synapse is the key that turns on the CD8 cytotoxic T cell. So now it is cytotoxic. It needs a redundancy. Where's it coming from? Here it is. This is the job of the type 1 helper T cell, is to release interleukin-2 to activate that clonal expansion of this activated cytotoxic T cell. Once that happens, clonal expansion takes place. We end up with some memory cells. Once clonal expansion has been activated, then the cytotoxic T cells become self-stimulating, meaning that they can release their own interleukin-2 and drive their own clonal expansion. So a lot of redundancy in here. Whoop. Not exactly what I wanted to do. Let's try it again. Oh, there we go. That was scary. Okay, now, how does this cytotoxic T cell kill an infected cell? Well, here's an infected cell. Okay, how do we know it's infected? Remember, it's going to present the antigen of infection on an MAC1 receptor. So here's the cytotoxic T cell. There's the MAC1 receptor from the T cell. There's the viral epitope from the virus. Here's the CD8 redundancy. Once that happens, that's it. This guy's going to die. Okay? And how's it going to die? There's two flavors. Okay? One is that the cytotoxic T cell releases perforin, which causes a pore, and then granzyme traverses that pore in the plasma membrane, and it initiates the induction of apoptosis. We've talked about this before. The other way is the so-called CD95 immunological synapse. The outcome is going to be the same. It's just how it happens. Here you need perforin and granzyme. Here you need a secondary immunological synapse, but notice that the same thing happens. You end up with apoptotic enzymes from the mitochondria coming together to form, to make a apoptosome and carry out the destruction of the cell and everything within it. That apoptosome does not kid around. In less than 10 minutes, you will not know that there was a cell anywhere around there. It will destroy every aspect of it. So this is incredible stuff. Okay. Okay. Now we're going to go into the activation of B cells. This is the second part. A little bit different. Here's our repertoire of B cells, CD4. Okay. None of them are activated. Okay. And this guy is going to undergo an MHC2 synapse because it's a B cell, not a T cell. T cells do MHC1 and B cells only do MHC2. Okay. And you can see that once this takes place, there's the MHC2 CD4 synapse. So 1, 2, redundancy. Okay. And now we're almost done. There we go. Here's our production of a type 2 helper T cell. Okay. Oh, 1 second. Okay. So to recap, here's our preferential antigen presenting cell, which is a dendritic cell. Here's our repertoire of helper T cells, type 2. We talked about the redundancy of the immunological synapse. Again, it's going to be, because it's a helper T cell, it's going to be an MHC2 CD4 immunological synapse. There it is. Okay. That and the introduction of interleukin 4 causes the differentiation of that helper T cell into a helper T cell type 2. So now this guy is functioning. Now that helper helper T cell type 2 causes the immunological synapse with the correct inactivated B cell. So there it is, MAC2, CD4, no surprise, okay? And it also releases interleukin 4, so the redundancy is double, right? You have the MAC2, then you have the redundancy of the CD4, and then you have the redundancy of the interleukin 4. And once you have all those redundancies, then this B cell gets activated into a plasma cell. Those plasma cells then start secreting antibodies because that's their job. Some remain as memory cells, and you can see immunoglobulin M there, and the class switching to immunoglobulin G. Okay, so this is clonal expansion of the B cell. And that is it for this chapter, okay? I hope you enjoyed it. Pay attention to the parts that I discussed that are in red, because that's definitely going to be in your assessment, okay? And have yourselves a wonderful day. Thank you.